Just wrapped up our time at APEC 2022 in Houston, a conference and expo widely viewed as the best place in the world to learn about cutting-edge technologies related to power electronics. The APEC conference sessions pretty much lived up to their advanced billing, and some of the coolest technology emerged during the plenary sessions. One presentation by NASA Principal Technologist John Scott covered the NASA Artemis program, an effort that aims to set up an infrastructure on the moon. As Scott explained, the power electronics used on the moon are going to have special problems because of the high level of radiation they'll see there. Basically what happens is that the ionizing radiation can cause a highly concentrated track of charged pairs to be generated in the semiconductor device, which interacts with surrounding depletion regions and electric fields as the free carrier concentration is restored to equilibrium levels. These resulting effects can include displacement damage of the bulk semiconductor material, ionization damage in the oxides of the semiconductor, and oxide semiconductor interfaces, and a number of what are called single event effects. This is a big topic in wide bandgap semiconductors right now, and there's a lot of hand-wringing in research circles about it. Inverter technology was also a big topic at this year's APEC. One reason was explained by the director of Georgia Tech's Center for Distributed Energy, Deepak Divan. He said it's becoming clear the utility grid is becoming not so much a collection of generators as it is a collection of inverters. These inverters feed power onto the grid from renewable sources such as solar arrays and wind turbines. To that end, Divan described one cutting-edge piece of equipment called a multi-port energy router that's envisioned as consisting of 500 kilowatt inverter building blocks. Each building block will be bidirectional AC or DC at every port and will essentially be an inverter switching in the 20 kilohertz range. As Divan describes it, the grid will eventually consist of literally millions of these inverters to a point where inverters themselves form the grid and can ride through transients and disturbances the way conventional generators do today. No question that advances like those envisioned at Georgia Tech will demand advanced converter technology, and there were many examples of progress in this area on the APEC exposition floor. An example was on view at the Power Integrations booth. There you could see a new LLC resonant converter that was 96% power efficient. An LLC topology turns a DC input voltage into a square wave via a switch network to feed a resonant LLC tank that effectively filters out harmonics and provides a sinusoidal-like voltage and current waveform. This in turn feeds a transformer that provides voltage scaling and primary-secondary isolation. The converter power flow is controlled by modulating the square wave frequency with respect to the tank circuit's resonance. In the power integration device, the LLC circuit is combined with a synchronous rectification control circuit that controls the LLC operation and synchronous rectification and avoids problems like shoot-through, where both power semiconductors in the bridge are partially turned on simultaneously. There's a power factor control circuit on the Power Integrations LLC that employs a gallium nitride transistor to reduce conduction loss in the switching. The LLC itself uses a FRED-FET for fast recovery epitaxial diode FET to minimize diode recovery time in certain points of the switching cycle. A point to note about sophisticated topologies like the LLC converter is that they use magnetic components that can be increasingly time-consuming to design, partly because the properties of the ferromagnetic materials that go into inductor and transformer cores are difficult to model. And the design of magnetic components can be difficult because it involves nonlinear equations that are coupled. Moreover, it's increasingly the case that the inductors on some of these advanced power circuits are the biggest components on the circuit board. No surprise then that finding ways to more easily and compactly design magnetics was a big topic at APEC. One particularly interesting development was described by Alexander Gerfer at Würth Electronic. Gerfer described using artificial intelligence and deep learning algorithms to predict core loss in power transformers and inductors, eliminating the need for the usual measuring equipment after the algorithm has been trained. He says the results so far have been promising, so who knows? Maybe future APECs will see core designs produced by not much more than an algorithm in the cloud. And those were some of the highlights at this year's APEC.